Jen, let me throw it over to you. What can you tell us about Water Research Foundation Project 4508? This is also WRRF 1314, and it's entitled Assessment of Techniques to Evaluate and Demonstrate the Safety of Water from DPR Treatment Facilities. And this is a project that involves a ton of collaboration, lots of utilities together working on this. Take us into this project and tell us what you're finding out.
Sure. Well, as we discussed earlier, most potable reuse facilities are designed and permitted based on an extremely conservative assumption of risk, intended to alleviate risk by the public in a somewhat uncertain context. To grow potable reuse, we need to find the right amount of treatment for each situation and the right monitoring tools to help propel implementation. We're co-leading this Water Research Foundation project and WRF project to evaluate monitoring tools for both planned and unplanned indirect potable reuse scenarios, as well as direct potable reuse. We're carrying out sampling and testing at both pilot plants and operational facilities. And these are utilities that really care about having safe water for their customers, and they want to be on the forefront of research and development.
So one of the things you're trying to do with this project is to develop guidance for utilities on monitoring, figuring out what monitoring schemes work best for different treatment trains in the potable reuse realm.
Yeah, exactly. We're looking at both conventional parameters like TOC for reverse osmosis or turbidity for filtration, as well as more complex bulk surrogates like fluorescence emission excitation matrices, which there's an example of one shown here in the middle of this slide, which can be used for characterizing the character of organic carbon. We're also looking at more kind of innovative or next level characterization methods such as biological assays for characterizing cellular response to complex mixture of contaminants. So there's an example of a result from a bioassay shown here on the right. Or actually, there's several bioassays shown, but the graph is showing as you move from left to the right. You're moving through the treatment train at a advanced wastewater treatment plant, and the results are shown sort of as a heat map where the red and the orange are higher response, and the green is a lower response, so less risk, cleaner water. So it's really interesting to be able to see how these biological responses to mixtures of contaminants can impact, the water quality and help us manage risk. So some of the endpoints these biological assays can help define or provide a context for understanding it are cytotoxicity, genotoxicity, mutageneity, and endocrine disruption, just to name a few. So in addition to these kind of grab samples that we would collect, we're also looking at innovative online instrumentation for assessing performance. An example of one of the probes that we're evaluating is Xylem's NicaVis, which is an instrument that uses a UV spectral scan to provide an indication of the total organic carbon, dissolved organic carbon, as well as COD and BOD in the water matrix. It can also measure nitrate and nitrite. So it's really exciting to be able to look at all these different tools in how you can characterize water quality. As part of the project, we're collaborating with 14 utilities that are located both within the U.S. and actually internationally as well. The majority of the utilities we're working with practice planned IPR, and several others practice de facto IPR, as well as direct potable reuse or non-potable reuse, or some combination thereof. So the graph here shown on the right is a summary of the different types of utilities that are participating in the project. We surveyed these facilities to see what standards of practice people use for monitoring for each different treatment train used in their process. So the graph on the right shows facilities. We've just anonymously identified them as numbers 1 through 14. So those are the 14 participating utilities. And the number of monitoring parameters are shown on the y-axis here. So you can see there's definitely a range in the number of monitoring parameters that are regularly conducted as part of monitoring for each of these utilities. The other takeaway that we got out of this was that there was no single parameter that was monitored at all facilities. However, the most commonly monitored parameters were conventional analyses like alkalinity, conductivity, ammonia, nitrate, turbidity, pH, temperature, things like that. So in addition to the historical data survey, we also conducted an expert panel workshop, and we're now conducting rigorous sampling at some of our participating utilities. We hope to distill this data into guidance that utilities can use for full advanced treatment process trains, including MSRO, UV, AOP, or those including biological treatment as part of the process as well, which would include ozone and, say, BAC, biological, granular activated carbon, or anthracite filters. So this slide here shows some conceptual strawman monitoring regimes that we are proposing for biological monitoring. Now, these are not final. They're just where we're at, the most up-to-date for where we're at with the project. Once we get the rest of the data in from monitoring at the full-scale facilities, we'll revise these recommendations. And we also plan to develop similar schematics for chemical monitoring. But this just gives you an idea of the overall framework that we're trying to develop. You can see here the different monitoring parameters that are associated with each treatment train. And those parameters shown in black bold are more of the conventional type parameters, and those in green are more standard biological analyses, and those in red are the more higher end expensive analyses, like pepper mild modal virus, that's the PMMOV, which can be used as an indicator of viruses that are not effectively moved through conventional wastewater treatment.